This presentation is about scanning electron microscopy for biological specimens by Group 7. Scanning electron microscopy, also known as SEM, is an instrument for the analysis of the microstructure, morphology, and chemical composition, and it is widely used to study structural details on the surface of biological samples. When it's at a relatively lower magnification, it can obtain a large amount of sample at once, while at higher magnification, it is able to get high-resolution images of that specific structure. In SEM, sample preparation is an essential step which must be carried out for an accurate result. The conventional sample preparation process includes fixation, dehydration, drying, and optionally conductive coating. Fixation is normally performed in aldehyde buffers, as they are used as a vehicle for the chemical fixative. This is followed by dehydrating with organic solvents to replace water, and then dried to remove these organic solvents. But these can produce artifacts in delicate biological samples, such as a change in protein localization. However, a quantitative characterization of the morphological changes caused by the steps is currently lacking.
The process of sample preparation for SEM differs depending on if the sample is dry or wet. If the sample is dry, it will go through the vapor fixation, which is easy but harsh, and if the sample is wet, it will go through the chemical fixation, which is a quick procedure. Then the dehydration to remove water. Both of the samples will then go through melting, coating, and finally the SEM observation. Electrons are made at the top of the column, pushed down, and pass through the combination of lenses and apertures to create a focused beam of electrons which hits the surface of the sample. The sample gets mounted on a stage in the chamber, and both the column and chamber will get evacuated via the combination of pumps. The position of the electron beam on the sample will be controlled by scan coils located above the objective lens. This scanning enables us to collect the information of the specific area. Signals will be produced as a result of the electron, and samples interact, and signals will get detected. SEM produces images by scanning the sample with a high-energy beam of electrons. The electrons interact with the sample to create secondary electrons, backscattered electrons, and characteristic X-rays. The signals get collected by detectors, which form images and are displayed on the screen. Although the maximum resolution depends on numerous factors such as the electron spot size, where, usually, modern-sized SEMs provide resolution between 1 to 20 nanometers.
Secondary electrons are low-energy electrons that are only detected when they are generated close to the surface of the sample. They have the best imaging resolution and are used to show the morphology and topography of the sample. Backscattered electrons are created when electrons in the electron beam arcs around the nucleus due to the electromagnetic force to come back out of the sample. The number of backscattered electrons is proportional with the size of the atom's nucleus and can be used to help analyze the sample's crystalline structure. Characteristic X-rays are generated when an electron moves from the outer shell of an atom into the inner shell. The X-ray photons emitted are unique to that element and hence can be used for elemental analysis. The use of electrons compared to light allows for a higher resolution and a finer detail of the sample. Hence, an electron gun is used to fire a thin beam of electrons at the sample. There are two types of guns that can be used, a thermionic emission gun and a field emission gun. Both have an electron source and use voltage to direct the electrons to the sample. A thermionic emission gun applies thermal energy to the cathode filament to emit electrons, whereas a field emission gun uses a strong electric field to pull electrons from a sharply pointed emitter. From the gun, the electron beam is then passed through a series of electromagnetic lines to modify the path and change the size of the beam. In the case of SEM, the lens can manipulate electron trajectory to form a small electron probe. The condenser lines converge the electron beam to the just size, which detects the resolution. The stronger the condenser lines, the smaller the resulting beam diameter. The objective lines converges the electron beam again to focus the beam onto the chosen area of the sample.
Development of a polymer nanoceramic composite material with potential application in biomedical engineering. This example uses SEM to characterize the microstructure of three different composition of the polymer and the nanoceramic material, along with the other dynamical mechanical analysis for further characterization. Agglomerates were identified in the SEM images, which indicate that the extrusion process during the development of the materials wasn't efficient in homogenizing. Differential scanning calorimeters determined the thermal transition of the materials, and a trend was identified where the increased percentage of the ceramic material reduced the crystallization temperature. Stress X stream curves were used to identify the decrease in mechanical resistance with the increase of the percentage of the ceramic material. It was concluded that the further research into the material's degradation was needed. Evaluation of in vivo adsorption of the blood elements onto hydro-coated silicon rubber by scanning electron microscopy and the Fourier transform inferred spectroscopy. This looked at the reaction of the whole flowing canine blood with four polymer surface varying in hydrophility. Data obtained by SEM and the Fourier transform inferred analysis was used to find the relative amount of the protein present and determine the type and amount of the adhering blood cells and fibrin. The knowledge of the protein deposition and the molecular configuration and the composition could be used to formulate a material that will be accepted by the body. Different degrees of the hydrophility was obtained by coating silicon rubber with three different hydroformulations. These materials were used as the femoral artery to vein shorted and removed after 15 minutes. They are then analyzed through SEM and FTIR, which includes scanning the samples with infrared light to observe the chemical properties. From the SEM micrographs and the FTIR spectra, the more hydrophility and the hydrographed surface, the less fibrin and cellular elements deposit on it. This trend remained similar across all dogs. There is also considerable variation in thrombus deposition, which is likely due to the progressive thrombus buildup and embolization. This is all the reference used by our group, and thank you for your listening and watching.